Okay, so we'll start for today. I hope my screen is visible, and can one of you just confirm whether am I audible? Okay, fine. So let us take the first question for today. It is technical question number 43 from GATE 2013. The following arrangement consists of an ideal transformer and an attenuator, which attenuates by a factor of 0.8, and AC voltage VWX1 is 100 volts is applied across W and X to get an open circuit voltage of V of YZ1 across Y and Z. Next, an AC voltage source, say VYZ2 of 100 volt, is applied from the other side of the circuit to get an open circuit voltage V of WX2 across WX. Then what is the ratio of the following voltages which we mentioned previously? So which are the options that match to this? So the two things are important in this question. The first one, it is mentioned that this is ideal transformer and an attenuator which attenuates by a factor of 0.8. So if someone doesn't know the meaning of attenuate means decrease. Basically it is a form of a loss of something. And open circuit is mentioned here. So this entire circuit will operate in an open circuit fashion. So let us bifurcate the circuit into two parts. One is the transformer and one is the attenuator. So when you go from right to left, this transformer circuit applies a multiplication factor of 1.25 to the voltage, and this attenuator applies a multiplication factor of 0.8 to the voltage as it is given in the question. Okay. Now during case 1, as we are moving from right to left, they say let us assume we give 100 volts as per the question. So intermediate voltage just after the transformer will be 125 by this factor, and by this attenuator again when you multiply 125 by 0.8 it will be 100. So as per the question, VYZ1 and VWX1 will be 100 by 100. Okay, so we have solved the first part of the question, which will be 100 by 100 YZ1 upon WX1, which will be either from the B option and the C option. Now let us look at the second part of the question, where they are saying 100 volts is given at YZ. What will be WX? So as we know, it is given as ideal transformer and it is an open circuit voltage. Open circuit voltage is taken in the question and it is ideal transformer. So no current will be drawn in the transformer during open circuit voltage. As there is no secondary circuit, it will not draw any short circuit kind of current or any load current, as secondary circuit is incomplete, and it is ideal transformer, so it will not draw any magnetizing current to set up the flux. In ideal transformer, magnetizing current is 0. So as there is no current drawn by the transformer, this voltage is simply at this winding on the secondary side. So 100 will come as it is at 100, and it will reflect as a 80% step down operation. So it will be 80 here. So VYWX2 upon VYZ2 will be 80 upon 100. So as per the question, the answer will be option B, 100 by 100 and 80 by 100. So any doubt in this question? From you guys? Okay, fine. Let us take the next question. So this is technical question 44 from GATE 2013. So a thyristor T in the figure below is initially off and is triggered with single pulse of width 10 microsecond. It is given that L is equal to 100 by pi microhenry and C is 100 by pi microfarad. Assuming latching and holding currents of the thyristors are both 0, the initial charge on C is 0. The transistor conducts for what time? So 10 microsecond, 50 microsecond, 100 microsecond, or 200 microsecond. So let us apply KVL to the circuit. So 15 volts is given, thyristor is there. Assume thyristor is fired and 15 volts come into the circuit. So the KVL of the circuit will be 15 equal to LdI by dt plus integral of I dt. Voltage across inductor, voltage across capacitor. Now let us take the Laplace transform of this and find the current through the circuit. So 15 by S is equal to SL plus 1 by SC into I of S. Now when we take this I of S and just reshuffle it from left to right, the equivalent circuit becomes 15 by L upon S square plus 1 by LC. Now if we rearrange to take the inverse Laplace transform and we substitute omega as 1 by root LC, which is given in the circuit, the inverse Laplace transform corresponds to some factor k into sine of omega t, where omega is, as shown in the previous line, 1 upon root LC. So I of t turns out to be a sinusoidal signal of positive duration and negative magnitude duration. So it's a sinusoidal signal. Now as again by rearranging the circuit, omega is equal to 1 by root LC. By substituting the values of L and C in the circuit, L is equal to 100 by pi microhenry and C equal to 100 by pi microfarad. So we get omega as pi into 10 raised to 4 and T is 2 pi by omega. So we get 200 microsecond is the time period of this sinusoidal signal. And as we know, thyristor only conducts in the positive current. It doesn't conduct in the reverse direction. It is kind of a control diode. So after T by 2, thyristor will stop conducting. So the thyristor will only conduct for till T by 2 condition. Okay. So the thyristor conducts for T by 2, that is our time period was 200 microseconds, so half is 100 microsecond. So the thyristor will conduct for 100 microsecond. Okay. So if it is triggered at time equal to 0, fine. So as it is not the triggering time of the thyristor is not given at what instant of this sinusoid is there. We assume this sinusoid has started once this 15 volt has come across the circuit, and the t equal to 0 is the firing angle of the thyristor, because this sinusoid is conceptualized, as in it is realized in the circuit only when thyristor started conducting. It was a DC signal that was fed to this circuit. So the sinusoid is a resultant when the thyristor came into the circuit, and that's why from this t equal to 0 till t by 2 thyristor will conduct and not in the negative direction. So t equal to 100 microseconds is for which the thyristor will conduct. So any doubt in this question? Okay. Yeah, so let's take a technical question 45, gate 2013. A 4-pole induction motor supplied by slightly unbalanced 3-phase 50 Hz source is rotating at 1440 RPM. The electrical frequency in Hertz of the induced negative sequence current in the rotor is. So when there is a unbalanced 3-phase system, there are positive, negative and zero sequence currents, and the characteristic of that positive, negative, zero sequence currents are negative sequence is in 3-phase only, which maintains the 120 degree phase shift between the individual 3 phases A, B, C, which are phase shifted by each other by 120 degrees. So let us take an example which is given in the question, where induction motor is fed by a 3-phase voltage source. So in a typical balanced supply which is fed to induction motor, the slip is defined by Ns minus Nr by Ns, where Ns is the synchronous rotating magnetic field, synchronous speed of the induction motor, minus Nr is the rotor speed of the induction motor upon Ns, as I said, synchronous speed. Slip signifies the relative speed of the rotor with respect to stator. Due to this relative motion, the voltage is induced, and the frequency of the induced voltage in the rotor is S into Fs, where Fs is the supply voltage frequency, which governs the synchronous frequency Ns. So this is for the ideal balanced supply of synchronous speed for the induction motor. This is the typical diagram where RYB is the phase, RYB in this fashion, and direction of the rotation is given for this. Now the slip of the induction motor is given by for ideal case when there is no negative sequence. For the positive sequence of the voltage, it is given as so a healthy power system always contains a positive sequence. There will be no negative and zero sequence component. So a normal system represents the positive sequence of the power system. So Ns is given by the formula 120 F by P, where F is equal to 50 and P is equal to 4, which is given in the question. So 120 into F by P will result in 1500 RPM, and slip will be, for the positive sequence, will be 1500 minus 1440, which is given in the question, rotor speed, upon 1500, which is equal to S equal to 0.04. So this is for the positive sequence, which is in case if there were no negative sequence, then this will be the power system's the behavior with the induction motor, where slip will be 0.04. Now it is said it is a little bit unbalanced system, so there is a negative sequence component in the supply. So the characteristic of a negative sequence is the rotating magnetic field, which I mentioned here. The direction of the rotation is opposite. So the Ns will rotate for the negative sequence opposite direction of the rotor. So typically the induction motor, the rotor tries to chase the rotating magnetic field, which is induced due to positive sequence. Whereas when a negative sequence is present, the negative sequence induces a magnetic field which is opposite to the direction of the rotor, or opposite to the direction of the negative, opposite to the direction of the positive sequence of the supply. So when we put Ns equal to minus S, Ns in the slip formula which I mentioned earlier in this formula, so Ns will become minus for negative sequence. So S negatives, which is slip in the negative sequence, it will be minus Ns minus Nr upon minus Ns. So it will be 2 minus S, where S is positive sequence slip. So S negative is 2 minus S. So the rotor frequency, as we said, it is slip into supply frequency. So we have S negative into supply frequency, which is 2 minus S into Fs, which is 1.96 into 50 hertz, which is supply frequency. So answer is 98 hertz. So this is the answer to this question, option B, 98 hertz for the induced negative sequence current in the rotor. So any doubts in this question? Okay, fine. So that's all for today. These are the 3 questions I planned for today, and we'll continue in the next class. Thank you.